recording. Yeah, so the recording has started, and okay, fine. So, hello and very good evening to everyone present over here. I am Shouharda Ghosh. Okay, let me write down my details also. So, my name is Shouharda Ghosh, and I am currently a second year PhD student in the electrical engineering discipline at IIT Gandhinagar. So basically, you have three TAs in this course. One of them is from, okay, so a lot of people are joining in. Wait a second. I can't see you who all want to join. Okay. Okay. So yeah. So I'm from I'm PhD student in electrical engineering department at IIT Gandhinagar, and you also I am one of the three TAs. The other TAs, other one of them is from IIT Kanpur, and I guess his session, or maybe the other one who is from IIT Kharagpur, his session took place yesterday, and there's another session tomorrow. So I'll be conducting these PMRF sponsored sessions every Monday from. Okay, so our sessions will be every Monday from 6 to 8 p.m. Okay, and let me tell you, this is a PMRF NPTEL session for the course Signals and Systems. So currently I'm a second year PhD student at EE discipline in IIT Gandhinagar. Okay, and I have also done my dual degree, that is BTech as well as MTech. It's a 5-year course with specialization in microelectronics and VLSI design at IIT Kharagpur. So I'm proud to be associated with two IITs. In one of them, I've completed my bachelor's and master's. I mean, it was an integrated program, and the other one presently at Gandhinagar, where I'm doing my PhD. Okay, so basically, okay, so engineering student, I'm having trouble. So what is the trouble that you are facing? Electrical engineering student, if you could say your name, that would be better. Week-1 assignment, fine. So we will get to that. We will get to that. So it's a 2-hour session, but then so I'll be covering all the previous year assignments and a bit of a hint as well as the concepts required to solve this week's assignment. So basically the course name is Signals and Systems. Okay, so before I start, I would like to know how many of you are okay, so I'd like to know your background. How many of you are first year EE students? First year students. How many of you are first year students? Please raise your hand, or maybe rather I can ask each one of you. Okay, so Pawan, could you please introduce yourself? Pawan Kumar Rapulu.
Sir, I'm studying in JNU Kakinada.
Okay.
I'm second year.
Okay, in which department? ECE?
Triple E, sir.
Double E. Okay, good. You are in second year, right?
Yes, sir.
So, do you have signals and system in this semester, or you have completed it before?
Sir, no, sir. There is no signal systems in our semester, in our BTech course, sir.
Okay. But it's good that you're taking it because are you because if you sit for GATE or other competitive exams, that's surely a part of all of them. Then you have Cherupu Shravan. Shravan, could you please introduce yourself? Shravan, are you there? Fine. Govindraj? No response. Uh, Lena Deely, could you introduce yourself? Fine. No response. I guess this is our first day, so at least we could get to know ourselves each day. We'll have a lot of time to clear our doubts, but then let's break the ice. Niketan Mishra, can you please introduce yourself? Okay. Rajkumar Durgada, Suraj Patil. Okay, fine. So, irrespective of the background, because although it's a live session, it is being recorded, and a lot of students will be seeing this from YouTube. Most likely, they'll be seeing this in a recorded version. So, how is this course important? Okay, so I'll try to emphasize that. So, the importance of this course from two perspectives. First, exams. So how is it important from an exam perspective? So you have this in your semesters, whether from EE, EC, IN, or whatever be the variants of electrical and electronics engineering. There are thousands of names, but essentially they are the same. And it's expected that you have one semester or a sem course in semester for the signals and systems course. Okay, and it's not only just about the semester, it's about the gate exam, ESC engineering service exam, then ISRO, DRDO, BARC, and other PSUs. This is a very critical and important subject for both um, the written exam as well as the interview. Even more, if you go for research, um, yeah, if you go for higher studies, let's say MTech, especially in courses like you have these specializations, like just like I did my specialization in microelectronics and VLSI design. So you have specializations like signal processing. So there are various variants like signal processing and communication, sometimes signal processing only, sometimes signal processing and machine learning, or signal processing and AI. Okay, so in all of these, your course of signals and systems forms a very big fundamental. And now from the applications perspective in real life, and I will show there's an indirect link also between these. So what is electrical engineering all about? You have some kind of a signal, you pass it through a black box which we call the system, and you get something out which is obviously a signal. So our signals of interest can be, what I'm speaking now is an acoustic signal. And what is the origin of acoustic signal? It's pressure waves. Okay, so these are pressure waves, so it's not an electrical signal. Okay, the twitching of my eyes, these movements, these are what? These are muscular. These are also signals. I'm showing you something with my hands. I'm signaling at you. Okay, so acoustic signals are there. Then you have then you have the optical signals like I will switch my camera on or light on. I send you flashes of photons, right? So sending a light on off, that's also signaling. Okay, so when you see a traffic light on off, so it's showing you some kind of signal. So what is signal? Signal is something that carries information. So information in various ways. I pinch you, okay, I some sorry, somebody pinches your skin, so that's also a kind of signal. It's a mechanical signal. You're pinching somebody. That information is initially in a mechanical form, then you have skin receptors get that signal, transfer it into neural signals, which are actually electrical in nature, and then a lot of chemistry goes in. So these are chemical signals. Okay, there are a lot of a great degree of biological signals. Okay. Okay, his understanding of situation, his understanding of a situation and output signal. Yeah, exactly. Nice. So I'll say you something. I mean, I've not covered in signal system, but there's something called cognitive science. Cognitive science actually models our the entire, let's say, an animal mind or a human mind as a kind of a system. And let's say you give some inputs to it. For example, you might be knowing about the Pavlov's famous dog experiment, which gave him the, I guess it gave him the Nobel Prize. So initially he was conditioning the dog, saying that whenever it rang the bell, the and the food used to be given to the dog, and the dog would come out and see that the food was given the moment the bell was rung. He kept on continuing this process, and in that process, the whenever the dog used to see that food, he would salivate. Now he could get the connection that the system is the dog's brain. The input is the actually the sound of the acoustic sound of the bell, and whenever he sees this food, he gets to drool, release the saliva. So now what happens one day, he just rings the bell, doesn't give any food, but what he found is that this dog started drooling automatically. So basically what is this? Is a signal and system. The output is the what you mentioned in the understanding of a situation. So this understanding of situation in terms of dog is the drooling of the saliva. Okay, so that's also the system based response. So another thing these days you see, it's the um, age of AI. So basically, so all these that I've been talking now is about signals, but we'll be dealing with electrical signals, which are basically in terms of voltages. We have lots of people joining in. Voltages and currents. Fine. So when you talk about voltages, so whatever we'll be dealing with in the electrical engineering phenomenon, we'll be trying to convert each of these: acoustic, optical, biological, whatever. There will be some kind of conversion phenomenon which we won't be dealing with into electrical, and we'll be dealing with electrical systems. We'll be dealing with resistors, capacitors, and all that stuff. Fine, that's in electronic engineering. And in other words, I was talking about the age of AI. So basically, you have these neural networks. So if I take a common example, day-to-day example of let's say the chat GPT. So at chat GPT, if you have if you're looking into news and bit into tech industry, you'll understand that this chat GPT is nothing called large language model. A model is what? A system. So this chat GPT is a large language model. You can treat this chat GPT as a system. What is the signal? The signal is the prompt that you type into the chat GPT. Let's say you want to write an absent letter of absenteeism for 2 days from your principal or from your HOD. So the prompt that you give, that please write a letter for absenteeism for next 2 days for dedicated to the HOD of your department. So that's the signal. The system is the entire neural, very big pre-trained neural network, which we call the chat GPT. um, so and then the signal, the output that comes is your well defined this leave letter. Okay, so how much space in GB does the system need? So what I say, although I don't work in this field of LLMs, but it's like space in the sense that I know that it has been trained upon trillions of gigabytes of data. um, I don't know about the storage, but then yes, it's humongous and it's concerning for the environment as well. So if you want to know about details of this chat GPT, so there are other parallel courses running in the computer science vertical, like applied artificial intelligence, or apply for the GPU based courses. So there you can get to know, or maybe you can type in chat GPT itself and check this answer. Fine. So back to our point, applications was signals get into systems, systems condition your signal, and you get a desired output or an undesired output. You have two things to do. Either you are trying to, one is analysis. What is this analysis? Analysis is you have this signal in the input side and the signal at the output side. You have both of these. Now you want to, oh no, sorry. Yeah, so you have the input signal and you have the output signal. Fine, yeah, you have them, you have both of them, and you want to see that when I change the system, how does the output change? Okay, when I tune some parameters, or I want to find what happens if I change this part. Okay, let's say this output system is known. Okay, system is known. Now I'm changing the parameters and then checking the output. Okay, this is analysis. And then the other one is synthesis. So synthesis tells us that if I have analysis is with systems that are already defined. Okay, so it's like you can't you have this in the human mind. Okay, so you can analyze the human mind, you can't synthesize the human mind. You give some inputs, you check the output, you see how you're modeling it. Okay, that's the analysis. And synthesis is something else. You have some input signal, you want some desired signal. Okay, now based on this, how do you design the system? That's synthesis. And basically your entire course, I'm assuming most of you are in your first or second year of your course, so based on that assumption, your entire degree will be revolving around these 2 points of analysis and synthesis. Fine. And now if you look into the later all the courses of your yeah, all the courses of electrical or electronics, since I my degree was in ECE. Okay, my degree was in ECE, not in pure EE, so I haven't done courses like machines and all. But even from that limited knowledge, you have courses like analog circuits or analog systems, you have digital circuits. So it's all about, in both of these cases you will learn about the two kinds of signals: analog signals, digital systems, and the systems which process them. Then you have a course called control systems. Control, you see the word system is inbuilt in it. It is about designing systems to control something. Okay, to control certain signals, certain parameters, certain derivatives of the signal. That's control system. Then you have courses like communication systems. So communication system and control system, these are two courses which build upon the foundation of signals and systems. So if you are good at this course, then you can easily fare through control systems and communication systems easily, in the sense that you will find a lot of things easier. In fact, in most of the courses of control system and communication system, a certain portion of the time gets dedicated in the revision of signals and systems once again. Okay, so the thing is that if you find signals and systems tricky, if you don't follow it or if you don't give this importance, then you're going to face a lot of hard time in understanding control system and communication system. And these control system and each of these courses in themselves become a specialization when you go for higher studies in MTech, and when you go into PhD, then each of them itself is a vast area of its own. How mathematically intensive is control system versus signal system? So as far as my experience goes, if you're talking about gate exam, okay, So gate exam, um, con- um, in terms of gate exam, I would say the control system is a bit more involved compared to signal systems, because control systems have a lot of other things to deal with in the stability and all. The mathematics are a bit more. A lot, most of the signals and system questions are such that you can do it without a calculator, and even if you will not require a calculator in most cases. If you, in some cases these are the trivial calculations, but control systems are a bit intensive. So that's from an exam perspective. And if you talk about research, I would say that please tell me the definition of signal. Okay, so what is signal? Signal is anything that carries information. For example, you just typed in a text. Okay, so this text can be a signal in various formats. So you try to convey a message. Okay, this message, the meaning of this message, that please give me the definition of a signal, is a psychological message in terms of its understanding, cognitive message. In terms of when you typed these messages onto your keyboard, when you're typing on this, these were, you're typing using hands, so you're applying force, so that's a mechanical signal when you're typing, pressing each of the buttons on your laptop. Now after pressing those buttons, these buttons had sensors beneath them, and based on the touches, these a circuit inside, or a small circuit or a small closed loop was formed inside the keyboard, which further led to propagation of electrical pulses into your entire computer system. And there's a computer architecture completely going into this. Please tell me your variables also. Fine, I'll tell you later. So when you press this, there's electricity going in, analog signal going in, and then you have something called ASCII, the American Standard Code for interchange of information. So basically you can represent 256 characters using this as ASCII code, which includes all our letters from A to Z and the special characters. So each of these numbers from A to Z can be coded in, I guess, 8 bits. So each of these bits, 8 bits number. Okay, so all zeros or all ones, they are by themselves electrical, they are digital signals. Okay, and when you transmitted them, when you press the enter button, it went from your laptop to my laptop. In the middle, what was there? There was the network. Okay, and in between it traveled from the Wi-Fi, the air. So how did it propagate? It propagated in the form um, of analog signal in the air. Fine, I'm not delving much into this, otherwise it would be a big discussion on its own. So what are variables? um, well, it's a bit confusing. By variables, do you mean the ones that you do in programming? Is that what you mean by? Okay, so variable, as far as I know, if you use any thing in MATLAB or either Python or C++, so it's something that's used to store the information. So you have a variable, say x equal to 2, and in the next step you do x equal to x plus 2. So that's a variable. Okay, x is a variable. It's almost like a it's almost like assigning, you, what you do is that you assign space to some registered in the CPU. Now I'm using words that are going outside the context. Yeah, Niketan, please. Your hands are raised up, so yeah, please let me know your doubt. Okay, fine. So variables are simply store some quantities which are used to hold on data. Simply, that's it. And it has as of now in this course there is no relevance of variables, but variables are important if you want to deal with signals and systems on computer. And yes, there's something called there's a course called digital signal processing, which is which grows on whatever you have learned from signals and systems. So DSP may be or may not be covered in your curriculum. Okay, I want to know about image, picture, and video signal. Um, let's do one thing. Since our primary objective is to cover the week's assignment, I'll be doing that first, and then I will keep the stage open for whatever doubts you have. So is that fine now? It's a very small, so I'll just be covering the previous year's assignments and a brief hint on the present week's assignment, because one of you asked that you have doubts or you're facing issues in week 1. So is that fine with all? I should I do the assignments and then I will continue with this discussion, because this is a never-ending discussion, and these are all quite open-ended topics. Okay, but let me tell you one thing: I won't be solving the assignment problems over here. Fine, I won't be solving the assignment problems over here. It's not allowed as per the NPTEL rules. I can just give you concepts or tricks to solve problems. So we will be solving the previous year problems. So the previous time this course was run, that was in 2022, I guess. Yeah, 2022, same time. Okay, so coming to problem number 1, says find the value of j sine hyperbolic x. Okay, so the question starts with a hyperbolic function. So before we start with hyperbolic function, let us look into the trigonometric function and their connection with the exponential functions. So the first and foremost relationship is the, yeah, I will look into. Okay, so you're saying sine hyperbolic. Uh, so, okay, wait a second. Let me start and then I will do, because everyone's people will see the recording as well. So I need to ensure that people get everyone learns things if they are not clear. So we have the Euler's identity, which states that e to the power jx is cosine of x plus j sine x. These are complex numbers, so you have something called the real part of the imaginary, the complex plane, and the imaginary part of the complex plane. And let's say we have a circle, which is called unit circle of radius 1 unit, and this x, it's e to the power jx, so the magnitude. So any complex number is of the form r e to the power j theta. R is the distance from the origin, and theta is the angle with respect to the x-axis. In this case, e to the power jx, the radius r is 1, and the radius means the distance from the origin. So in case you feel I'm speaking a bit fast or getting a bit too slow, please let me know. Okay, so is my speech proper? Am I speaking too fast or too slow? Please let me know in the comment section, or you can switch on your microphone and let me know. Fine, I will assume that my speed of speech is fine, and your theta is x. So what is this? Angle x. The coordinates of this point are cos x comma sin x. Fine, this length is cosine of x, this length is sine of x. E to the power jx is cosine x plus j sine x. Fine. Now if I put e to the power minus jx, I'll assume that you know certain things, because these are fundamentals that have been covered in class 11 and 12. So I won't get deep into that. I'll be revising them, but I will not be proving them. For example, e to the power minus jx, so that is cos of minus x plus j sine of minus x. Now I'm sure you know these properties. So what will happen? Cosine is an even function. What is an even function? I will let you know. You have these properties. Okay, so this equation 1, this equation 2. Let me add equation 1 and 2 first. If I add 1 with 2, what do I get? E to the power jx plus e to the power minus jx gives me cosine and cosine add, plus j minus j sine cancel. So we have cosine x equal to half e to the power jx plus e to the power minus jx. Now if I do 1 minus 2, I get e to the power jx minus e to the power minus jx, that's 2j sine of x. Sine of x is eventually 1 upon 2j e to the power jx minus e to the power minus jx. You should, these things should be in your fingertips, because later when you will be doing advanced problems, okay, these tricks, these identities will come in handy. Sorry. Okay, so that's about sin x. Now you have a special function called the cosine hyperbolic of x. And what's that? E to the power x plus e to the power minus x upon 2, and another function called the sine hyperbolic x, that's e to the power x minus e to the power minus x upon 2. You see a special feature now. Substitute cosine hyperbolic x with e to the power jx. What do you get? E to the power jx plus e to the power minus jx upon 2. What is this? Just, oh sorry, just check this. This is cosine of x. So I guess when somebody was asking about this, you can raise it to the doubt, ask a question section in the NPTEL. I mean, somebody was asking this question, right? That the options are not matching. Electrical engineering student. So in case you are here, or in case anybody is here, so what you can do, if you are feeling that it's not correct, or it's no option is coming up, then you should raise the matter to the NPTEL doubt forum, which I am sure you are aware about. Similarly, if I replace x by jx, what do I get? E to the power jx minus e to the power minus jx by 2. Let's be a bit careful over here. Here it's sine hyperbolic jx, but then sin x is 1 upon 2j, right? So what should I do? This will be j sine of x. Is that fine? So when you are asked to do j sine hyperbolic x, how would you go about it? J sine hyperbolic x is j times e to the power x minus e to the power minus x upon 2. Okay, so actually you require the options, otherwise it's not possible. So the options were actually sine jx, cosine jx, cos hyperbolic x, and minus sine hyperbolic x. Of course option D wouldn't make any sense, because that would mean j equal to minus 1, which is not the case at all. So How do you approach this? You see, there's in the options, what do you have? You have minus sine hyperbolic, you have cosine hyperbolic. Now, what is cosine hyperbolic? Cosine hyperbolic is e to the power x plus e to the power minus jx. Okay, these two are there, but here you have e to the power x and sorry, cosine hyperbolic has a plus, but here's a minus, and you have no way to bring in a plus over here. So what do you understand? It can't be even cosine hyperbolic x. That means we are left with sine and cos, and when you're left with sine and cos, it means you need to bring in the j's. Okay, you need to bring in the j's. How do you bring in the j? What is the property of j that we will be using? We will be using j square equal to minus 1. J, I mean, when you are in engineering, you replace the I that we learnt in class 11 or 12 as a complex number with j. And why was this done? This was done because when in engineering, when we start solving KCLs and KVLs or advanced circuits, we use I, small letter I, often for the current symbol. And when we deal with currents in complex scenarios, in complex in the sense AC currents, okay, so that time when you have phase shifts due to capacitors, inductors, you will be writing the complex inductance or the complex resistance, complex impedance as 2 plus ji, 2 plus i3 and something. So I into I, that would be a bit problematic. Niketan, you raised your hand. Niketan, any doubt? No. Yeah. If you have doubt, please raise your hand, or you please open your microphone. Sorry, no, yeah, switch on your microphone. So you need to bring j square equal to minus 1. So minus j square equal to 1. So what should we do over here? We have e to the power x. So plus it's positive, so we need to put minus x. So e to the power minus of jx minus of e to the power, that's minus 1, so j into jx. Okay, so now okay, so that's j e to the power x, e to the minus e to the power minus x. So what do you have? J, okay, minus j upon 2 e to the power j times jx. So I am taking out the minus sign from here, minus e to the power minus j of jx. Let me write theta equal to jx, that would be easier. So minus j upon 2 e to the power j theta minus e to the power minus j theta. So when you have minus j above, that will be 1 upon j below. Okay, why? Simply follow from this. One upon 2j e to the power j theta minus e to the power minus j theta. So what's this? Simply sine theta. And what's our theta? Jx. Sine of jx. So your correct answer is option A. I hope that's clear with everyone. If anybody has any doubt, please raise your hand or type in the comment box. Now let's move on to the second question. That's oh, thanks. Find the value. Yeah, it may look impressive, but then you guys also have to learn these impressive things, because you need to get impressive marks in your exams as well as in the competitive exams as well. And it's not about exams as well. These impressive things come in very handy in research as well. When you see research papers, you find that there are small tweaks done, and great results come out. Find the value of cosine hyperbolic x. The options were cos x, cos jx, sin x, minus sin x. Okay, so now what we should be doing, once again, e to the power x plus e to the power minus x upon 2, that's what we told earlier, cos hyperbolic x formula. Now again that substitution, so-called impressive substitution. Now j square equal to minus 1 plus e to the power jx, theta equal to jx, e to the power minus j theta plus e to the power j theta, back to our old form. Which old form? This old form, e to the power cos x, so it's cosine theta, so that's cosine of jx, so it's actually cos of jx. Yeah, correct, that's option B. Now our third question that was provided was delta 8t equals, okay, the options were 8 delta t, B 1 upon 8 delta t, C delta t upon 8, D delta upon t. So a brief recap into the delta function. So delta function is actually, you can't call it a function because it's something called the delta distribution. We just say delta function for the sake of simplicity, because it has a lot of absurdities that are not shown by normal mathematical functions. So a delta function in its simplest form can be represented by a rectangle which has a width of epsilon centered around 0 and a height 1 upon epsilon. So, and this epsilon happens, let's say this waveform, I call it PE of t. PE of t is a rectangle with an area 1 with a width epsilon and height 1 upon epsilon. Now as epsilon tends to 0, what will happen? Okay, I understand, but actually I'm revising the concepts as well, so that's why I am re-emphasizing this. So as epsilon becomes smaller, the width becomes smaller and the height becomes larger, and it tries to touch infinity. So limit epsilon tends to 0 PE of t, that then it becomes delta t. So we often say that delta t is a function which is not equal to 0 at t equal to 0, it's equal to 0 at t not equal to 0, and integral over minus infinity to infinity delta t dt is 1. Another very interesting thing is integral over a to b delta t dt is 1 if a lies between 0 and b. Fine. So if my impulse is situated anywhere over here and my limits of integral are between here and here, I'll get a 1. If I'm between here and here, I'll get a 1. But if I am somewhere here and here, I'll not get a 1, I'll get a 0 because I have not captured the impulse. So I'll use this property to find the delta 8, any arbitrary delta a of t. So let's do something. Let's try to find the integral over minus infinity to infinity delta at dt. What we will be doing over here is substitution of variables. Let's say x equals at, and our what will happen, dx equals to, the a is a constant, so it comes out, we get dt. So we substitute dt as dx upon a, and when t was minus infinity, x also becomes minus infinity. Simple multiplication. A is positive. Very important to note, a is positive. When t is infinity, x is infinity. Fine. So now when I substitute these values of the upper limits and lower limits, delta x dt was dx upon a, that was 1 upon a, integral minus infinity to infinity delta x dx, and that's 1 upon a. Now you look at this. Integration of minus infinity to infinity delta at dt equals 1 upon a, and that can be written as 1 upon a into 1. So I'm just getting back to this step. 1 upon a integration minus infinity to infinity delta t dt. Rather than next, we are back substituting our original variable. I put this a inside and I get delta t upon a dt. Now what do we do? We have delta at over here, we have delta t over a over here, and what do we get finally? Delta at is 1 upon a delta t. And even if it's, I leave this for you as a homework, even if a is negative, what you will finally get is delta a of t is minus 1 upon a delta t. So in general, what do we write? So if a is negative, negative negative cancels, you get the magnitude. So delta at is 1 upon mod a delta t. Very important. So what do we get? Option B. Yeah, somebody has switched on his mic. Yeah, Torati Tejaswini, do you have some doubt? Fine. Now let's get on the fourth problem. So the fourth problem is a very simple one. Cosine x is a odd signal, even signal, nothing or not defined, and whether it's a stochastic signal. So a bit of a revision over here. What kind of a signal is it? For an odd signal, the property that needs to be satisfied is that the negative of the argument, means f of minus x, is minus f of x. So when you try to look at the graph, if you have something like this, you have its opposite reflection on the and diagonal opposite. For an even signal, you have, okay, let me wear my spectacles, f of minus x equals f of x, that's even symmetric. How does it look like? It's symmetric about 0. So whatever you have over here, this acts as a mirror and you get the same thing over here. So for cosine x, if you have, as you very well know, cosine x looks something like this. It has its peaks at 0, 2 pi, and other even multiples of pi. At odd multiples it goes to -1, and at odd multiples of pi by 2 you have the 0 crossings. Okay, you have done this in your class 10 and 11, 12 as well. So you can see over here it's symmetric around this vertical axis, so it's an even function. Now what's a stochastic signal? So whenever I ask you to draw a cosine or a sine signal, you can always draw it. You know what is this waveform. So it's something called deterministic signal. That means given any time instant you can always draw it. But let's say you are asked to take a resistor and place your oscilloscope probes across the resistor. You will be able to see noisy waveforms. How will they look like? See, this is the oscilloscope, so they will look like this for some instant. After some instant it will change. Okay, so you see it's continuously changing, and at the same instant time you cannot determine what is it actually. So these are called stochastic signals that do not have any deterministic property. You cannot exactly draw a signal at a given point of time. Okay, so yes, how do you define such a signal mathematically? So when you have to define such signals, we use the statistics of the signal. Okay, so we use properties like the mean, the variance, etc. Okay, so when you learn probability and statistics course, after you go through that, then you'll be easily able to deal with random signals and systems. So you'll be covering random signals and systems in the communication systems course. We won't be covering stochastic signals in this course. Okay, so that's fine. Then you had another question, which was the second order derivative of fx equal to x log x. So we'll be applying the multiplication rule first. So fx is the product of x and log x. So in most cases, if from the options will be very clear that whether the log means log base 10 or it's log base the natural log. So you should be careful about that, and that will be easily visible from the options if it's not mentioned. So most of the time I would suggest that you directly go with ln when you're dealing with signals and systems and or something like that. In others, depending on the course, it varies from course to course which log is more suitable or which log is more popularly used. For example, if you are dealing with control systems or analog electronics or some portion of communication systems, they deal with log base 10. So when you're dealing with decimal voltage scale, it's more common to see ln periodic signals. I don't know any periodic signals that I've seen long to a very high. Dorothy, do you have any doubt? You raised your hand. No, fine. Okay, so now we do its derivative. So when you do f prime derivative, so we hold one of them constant and differentiate the other. So first we differentiate x keeping log x constant, and then we differentiate log x keeping x constant. So derivative of x is 1, and derivative of log x, I am assuming that's ln x, and that's what the option shows. Derivative of ln of x is 1 upon x. So what you get is log x plus 1. So difference between log and ln, nothing, it's just a scaling factor. So when we in general when log is a general term for the logarithmic function. Ln especially means log when your base is e. Okay, log when your base is e. So how will the graph of ln look like? Ln of x versus x. So all log functions will pass through 1, 0, but the point at which they become 1, that's difference. For ln it is e comma 1, for log it will be 10, 1. For any log base a it will be a comma 1, the point at which the ordinate or the y value becomes 1. Fine. Now our next question is integral over sine 3x into cosine 4x dx. It's a brief revision of whatever mathematics we have studied in 11 and 12, because we will require them a lot in these courses. So engineering is a very big carry forward of whatever you learned in 11th and 12th, and an extension and to that. So we use the property 2 sine a cos b equals sine of a plus b plus sine of a minus b. Fine. So what is a over here? Thrice x. B is 4x. Is it getting boring? Anybody or not able to understand anything, please let me know. So a plus b is 7x, a minus b is minus x. So what will be sine 3x times cos 4x? It will be sine 7x plus sine minus x upon 2, because here we don't have the 2, it will come in the denominator. So what we have over here is, let me take out the 2. So I have sine 7x plus sine minus x dx, that's half sine 7x minus sine x dx. And then what will you have? We know integration of cos x dx is sin x plus c, and integration of sin x dx is minus cos x plus c, and integration of f of kx dx is 1 upon k integration of f of x dx. So we have 7 over here. Our 7 will come out and we'll have a minus cosine of 7x. Similarly, we have a 1 over here, so and we have a negative sign, so minus of minus cosine x and then the c. So minus minus plus cosine x upon 2 minus cosine 7x upon 14 plus c. Okay, so I hope this is very clear to all. So this was our 6th question. Now let's go to our 7th question. So our 7th question says that when two capacitors C1 and C2 are in parallel, what is their equivalent capacitance? Now I will not share the answer with you directly. I will share the concept which is helps you get that actual answer, that helps you get that formula. Okay, so when you have two capacitors C1 and C2, these are in series. Okay, I'll do it for both series as well as parallel ones. Fine. So in series, what happens? The current or the charge is common to both. This current I1 or Q1, I2 or Q2, because they are connected in the same line, no? So when you're putting water through a, when you're pushing water through a pipe, then the flow rate in the pipe is constant. Why? It's because you cannot create water. You cannot suddenly put water in between. Water cannot get created or water cannot be consumed in between unless you have an external joint in between. So the joint actually represents the, yeah, I'll show you why. I'll show you why then this actually comes. Now let us denote the voltage across this as V1 and V2, and the equivalent voltage across this as V. So what is the relationship that we will be using? The current across the capacitor is the capacitance and the derivative of the voltage. Fine. So I1 and I2 are equal. Fine. When either I1 and I2 are equal, or you can say Q1 is also equal to Q2. Fine. So let's do in terms of currents first. So I1 is C dV1 upon dt. I2 is also okay, C1 C2 dV2 upon dt. So we say I equal to. Now what we also need, this entire, I should use a different color now. This entire system behaves as an equivalent capacitance Ceq, through which the voltage is V and current is I. So we have I equal to C equivalent dV dt. Now what do we know about the voltages? V equals to V1 plus V2. Alright. Now we differentiate them. dV dt equals to dV1 dt plus dV2 dt. And what is our voltage derivative if we see from this model? dV dt is equal to current upon C. Any doubt as till now, anywhere you are feeling any confusion, please let me know, because it's a very important concept. No, generally people learn this by heart, but they don't understand how this formula came into picture. So when you have this dV upon dt, dV upon dt is due to this total current or the current that is flowing through the through this combination and the equivalent capacitor in effect. So what will it be? I upon C equivalent. And what is dV1 upon dt? As you can see over here, this is the same I by C1. What is dV2 upon dt? Same I upon C2. Now you remove the i's from there. 1 upon C equivalent equals to 1 upon C1 plus 1 upon C2. So how does it come into picture? It's actually the conservation of charge. Conservation of charge as well as voltage. So it's, you have applied Kirchhoff's current law and the voltage law as well, because you are, no, not voltage law, because you're going in a closed loop. So that's for your series connection. Similarly, in parallel, what is happening? There's an equivalent voltage V0. There's a current I1. There's a current I2. There's a capacitance C1. There's a capacitance C2. This is equivalent to current I, equivalent capacitance C, same voltage concept here. Yeah, so we will use same voltage concept. Correct, absolutely correct. So what will happen? I equals to I1 plus I2. Fine. Now what is I? I is our C equivalent times d dVo upon dt. I1 is C1 times dV1 upon dt, because it's the same voltage across this. I2 is C2 times dVO upon dt, so dV1 is voltage are the same, so same voltage, so we cancel out the dVs and I get C equivalent is C1 plus C2. That's for parallel. The same thing could be done by replacing current with charges, because I is simply dq upon dt. So, but in that case, you should be a bit careful. You should assume that the capacitors are discharged. The initial charge stored across them is 0. That's the biggest assumption that you make. If there's some charge inside that, then these relationships won't hold true. Okay. So that was our 7th question. Let's go to the 8th question. And that's evaluate does that assumption hold for both relations. So actually when we deal with the zero initial charge, when I've used all of these, so I equal to C dV dt when you use that. Okay, so actually I would rather say that equivalent capacitance will formula actually remains same everywhere, but the procedure that uses Q instead of I. Okay, so since I had a derivative in it, and the derivative does not removes the condition of the initial charge and all. Okay, so that's why these things did not come into picture. But if you try to use charge based concept, so that charge based concept will require to assume that the initial charges. Yeah, are you saying something? Amazing. So when you are looking into the other one, the charge concept, that time you have to assume that the Q0 is coming into picture, because what will happen is that initially the voltage will not be V2 anymore. That voltage will be V2 plus the will have a concept will have a contribution of the earlier stored charge. Yeah, so actually we use the I based concept because when we will be dealing with the charges and when we'll be dealing with all these currents, no, so we won't be dealing with static conditions and all. We will be dealing with signals that are changing, not these DC cases. So in such cases we'll be using the derivatives actually. So later when we'll be dealing with Laplace transforms and all, that time we'll see how to deal these cases. So our 8th question is evaluate limit x tends to 0 square root of x square plus 5x plus 5 minus square root of 5 upon x. Now first things first, in every limit question you're supposed to check both the numerator and denominator individually. Okay, so let's check the numerator first. If I put x as 0, what is our numerator gonna be? 0 square times 5 times 0 plus 5 minus this thing turns out to be root 5 minus root 5, that's 0. Let's look at our denominator. What happens to the denominator when it's 0? It's simply 0 because that's x. So your numerator upon denominator is something of the form 0 upon 0. So we use something called the L'Hospital's rule. We actually don't call it L'Hospital, it's called L'Hopital. Okay, it's an Italian name, L'Hopital. So the hospital's S is not used, it's Hospital. So when you use the L'Hopital's rule, so it's applicable only when the numerator upon denominator is of the form 0 by 0 or infinity upon infinity. Okay, we won't be dealing with advanced cases which are taught in coaching institutes in JEE Advanced as we did in class 11 and 12. Okay, so don't worry about these anymore. So what does the L'Hopital's rule state? It states that for any limit when x tends to a, fx upon gx, if f of limit x tends to a, f of x equals 0 and limit x tends to a, g of x equals to 0, or if it's equal to infinity, both of them are 0 or both of them are equal to infinity together. So this can be evaluated as limit x tends to f prime x upon g prime x. If you see that both of them are again of the form 0 upon 0, then you can again apply it. You can keep on applying it only if you see that is of the 0 upon 0 form. Okay, you can't apply L'Hopital's rule if it's 0 upon infinity or infinity upon 0 form. That means that the function will diverge. There is no limit. Fine. So let's look back at this. There's a more interesting thing over here. There's something called the rationalization which you have learned in class 8 or 9, and I'm sure. So what we'll be using over here, let's check. Let's use that better. Whenever you see square root and all these plus minus things, always try to use rationalization rather than L'Hopital's rule. Square root of x square plus 5x plus 5 plus root 5 square root of, so we are multiplying it by its conjugate. So this of the form a minus b times a plus b, that is square minus b square. So you open up the roots, x square plus 5x plus 5 minus 5 by x times this thing. I am just putting it in brackets for now. I simplify them, 5 and 5 cancels. We have x square plus 5x in numerator, x times this something in the denominator. I further simplify x plus 5, x times something. Now let me put up this thing, x square plus 5x plus 5 plus root 5. Now you put in 0 and check. It's 5, it's root 5, it's root 5, it's 5 upon 2 root 5, it's root 5 upon 2. Does anybody have any doubt in this? I just did it a bit fast because unfortunately I am used to doing these things since long time. But if anybody has any doubt, please let me know. I could have used the L'Hopital's rule, but because there was this square root kind of thing, you should always prefer to rationalize stuff so that you can easily do cancellation rather than finding derivatives. Because if you do square root of x square x plus 5, if I had done that, what would have happened? If I had used L'Hopital's rule, the derivative of that would be 1 by 2 to 1 upon root over x square plus 5x plus 5, 2x plus 5 minus 0 divided by 1. Okay, that's also good. 5 by 2 root 5 upon 2. So this was a favorable case wherein if you had done L'Hopital's rule, if you are adept with doing differentiation and integration fast, that's good, but be careful. Yeah, okay. So that was our question number 8. So how many questions? Okay, so we've covered a lot of things as of now. So now let's look at the last question. Question number 9. We have to evaluate e to the power x. Okay. So now what we'll be doing, we have to expand it in the form of Taylor series in general, or in particular Maclaurin series. When you talk about Taylor series expansion, you expand it around a arbitrary point, a general point. And when you talk about Maclaurin series, it's a special Taylor series where you expand the function around 0. So what does the Taylor series say? The Taylor series says that f of x can be written as f of a plus x minus a times the first derivative of a plus x minus a whole square upon 2 factorial times f double prime of a plus x minus a whole cube times 3 factorial times f triple prime of a, and so on. And if you would like to see much cleaner stuff, we write f of x summation over k 0 to infinity x minus a to the power k, the kth derivative of f evaluated at x equal to a divided by k factorial. So it's a compact representation. Now that's your Taylor series, and Maclaurin series is f of, let me change the color, f of x equals summation over k equal to 0 to infinity x to the power k, k factorial dk fx dx to the power k evaluated at 0, which also becomes f0 plus x times f prime 0 plus x square upon 2 factorial f double prime 0 plus x cube upon 3 factorial times f triple prime 0, and so on. This is our Maclaurin series. So if you have e to the power x, that's your fx, f prime of x e to the power x, f double prime of x is e to the power x, and as you go, all the kth derivative of x will turn out to be e to the power x. So what will f of x be? F of 0 is e to the power 0, that's 1, times x times f prime of 0, that's 1, plus x square upon 2 factorial times 1 plus x cube upon 3 whole factorial times 1, and so on. So you have 1 plus x square upon 2 factorial, x cube upon 3 factorial, and so on. Okay, so that was the last question of the previous year's assignment, and based on this you can easily solve why is expansion being done. Okay, very good question. So much later you will be able to learn, if you do some advanced courses, you will learn the importance of Taylor series. What happens is that in engineering, in real life, all our systems are non-linear. So in our signals and systems course, we will have a section where we'll be dealing with linear signals, linear systems, or non-linear systems. Okay, we'll try to classify the system based on its linearity and check, apply tests to the system and check whether it's linear or not. Okay, so in real life, almost every system is non-linear. Now, what I mean, so for example, if I want to explain to you what linearity means for now, not from systems perspective, in general, let's say you have a resistor, the voltage across it is VR and the current to it is IR. So when you plot VR upon IR, you know the very valid Ohm's law. Because of this Ohm's law, your VR is directly proportional to IR. Okay, but you have certain devices, let's say diodes, which you will learn in your electronic devices course as well as or your analog circuits course. So this diode is actually the first nonlinear system that we will be learning in detail in any EE course. So if you look at the ID versus VD characteristic in real time, I'm drawing the real graph. Not there are various approximations to this graph, but I'm drawing the real graph. So what happens? It has an exponential behavior, e to the power x. It's not a x, it's e to the power x. And when you go back, it does not allow current to flow. Very low leakage current it allows to flow. And then after a certain voltage, the diode breaks up and allows any current to flow through it. So what happens is that, let's suppose I use some big circuit, okay, resistors, capacitors, and along with that I use a diode, okay. Now let's suppose this is the input signal. We also call it the excitation, okay, excitation. Now let's say my input excitation is very large, okay, like this means it voltage goes up to this, so it means current can go between this any range, okay. So you see I have to use this, and how does the equation look like? I'll show you. ID is some constant times, as your courses progress you will be able to understand the meaning of each and every symbol, times exponential of this voltage times certain other constant minus 1, okay. So this actually models everything up to this part, fine. So when my excitation is in this range, okay Niketan, I will come to that. So ID equal to is exponential this thing. So when this thing is large, that time what happens is that your signal, you have to use this nonlinear equation to solve the currents or voltages that are present inside the network, inside this system, okay, in order to analyze that. But in a lot of cases, the signals that we use in our real life, or the signals that we acquire from the environment, okay, so they are very minute, okay. So what may happen in reality is that if you have this diode, your actual signal may be something like this. Can you see this? It has a fixed constant value and it is oscillating around a certain point, okay. So if I zoom in on this point, let's say it has a fixed voltage, our signal is like this, V in, it's around a fixed DC and it is fluctuating with a small value, okay. So if I zoom into this, what do I actually see? This is V0 and let's say my signal variation is delta. So this goes over delta by 2, this goes over delta upon 2, and your output will actually vary along this. So what you actually see is that in lot of cases the signal that you are applying is very low fluctuation, okay, and the fluctuation is to an extent that you can assume that this range, okay. So I have magnified this exponential curve, so within this range you can see it almost behaves like a straight line. And how does it look? It looks linear, isn't it? And now you see what am I doing? I am doing a Taylor series expansion around which point? Around V equal to V0. So what is this? ID is a function of VD. And what are we doing? We are doing a Taylor series expansion around VD equal to V0. Okay, Taylor series. And in what happens, you need to Taylor series and we analyze such systems. We assume that higher order terms like the double derivative, triple derivative, all of them become zero. So what happens in such cases? You can approximate your function as f of a plus x minus a times f prime of a. Okay, it's a linear system. Okay, and analyzing linear systems are a lot easier compared to linear systems. Okay, so that's why we use Taylor series in a lot of cases. You will learn the concept that I've shown over here. It's something called the small signal analysis. Okay, you will learn small signal analysis in great detail in your analog circuits course, where you will be dealing with electronic devices, where you take in signals from the outside world. Okay, small juggling signals like the small signals, and then you amplify them to a larger value. Okay, look at, you will study them later, but the main point to draw is that the point of interest is the b naught. What is the significance of x equal to 0 in Maclaurin series? So yes, Maclaurin series is nothing but it's a special case of Taylor series where you're expanding around 0. So if your point of interest or a point of voltage is 0, so that time it's a Maclaurin series. Otherwise it's nothing special, it's just for a equal to 0. So Taylor series is the crux, Maclaurin series is a special. Okay, so why we call image is a signal? Okay, two answers to this, one in terms of the general. Okay, so Niketan, so if somebody sends you this image on WhatsApp, let's say you ask somebody how are you. Okay, you ask somebody on how are you and you get this, you get to know something about that person's mood, right? If he sends you something like this, you also get to know something like this, right? So this is why, and what do you get to know? You get to know information. So basically you are getting information through images, and that's why we call signal as a information. So let's suppose somebody waves his hand towards you, that's also a signal. Okay, now that's a generic way, that's a signal. Now, and who is processing that signal? What is the system? Your mind. Your eyes are perceiving the motion of your hands. There are lots of nervous cells and biological systems which go into processing that waving of the hands down to your cognitive systems. That's in one sense. In other sense, if you want to look at it from an electrical engineering perspective, let me use this WhatsApp thing. Okay, when you look at the image, or even if you're looking at a computer screen, okay, the images are not continuous, they are actually discrete. So how does an image look like? So you have something, okay, so what happens is that your screen consists of small blocks. Okay, each of these blocks has a sensor beneath it. Okay, this is what I'm saying is the actual scenario. And even mathematically, you know a matrix, right? An m cross n matrix, isn't it? There are m rows and n columns that can be filled with numbers. Okay, now at this array, at each element you place a sensor. Okay, and now you replace, let's suppose you have an array, and that array can have all the elements of the array can assume values between, let's say, 0, 1 2 all the way till 255. Okay, so these are integers. It can take integer value, and depending on that integer value, the sensor will glow. So if it's 0, the sensor will not glow. Sorry, it's not a sensor. So I was talking about a camera. So let's say you have an LED. Okay, LED, and this 0 to 255 defines the brightness of the LED. So if it's 0, so it's a dark, it's completely dark. And if it's 255, it's completely white. If it's something in the middle, so that's grayscale. I'm talking about black and white images. So if you want me to draw an image for you, so let me fill this up. I can't fill this up too nicely. Please assume that they are completely black. Okay, billions of colors with 256 values for an element. Okay, I'll come to it. I'll come to it. So what happens is that, okay, let me so let me, I think I have to go to Google then. Pixelated. Okay, so you can see this Mario over here, right? So Niketan, you get a signal over here, right? Immediately you look over there. If you look into this individually, there are unfortunately I cannot write I can't write over here, but yes, you can see these blocks. Each of these blocks are like the array matrix. This entire white thing, this entire image is a like an array, and each of these squares are like the pixels. Okay, so you fill certain pixel with a full black, or this is a completely binary image. That means either it's a 1 or a 0. So what I told was a 255 to 0. That was an intermediate black and white, the grayscale image that you used to see in your grandparents' photographs. Okay, so that's what is happening over here. So you have all these array cells that are filling up the. Okay, so what is happening in other words, you have this entire rectangular array. These rectangular array elements are filled with either ones or zeros, and if it's a 0, it's a black square. If it's a 0, it's a white square, and based on the positioning of this black and white, you finally get to see the entire image. How do I even get back? So this one is an ice cream. So this one is an ice cream. So you can see all these black and white pixels over here. So it's a pixelated image. So in fact you can convert this into a matrix of ones and zeros. So in a mathematical term, if you want to look into the mathematics, so you are actually looking at an array, an m cross n array filled with integer entries. That's a signal, a mathematical way of describing a signal, a matrix X. That was the pure black, the binary image. Okay, binary scale image. Then there's grayscale image. Okay, so let me show you pixelated grayscale images. And you see, not all images make sense. So if you fill up the arbitrary black and white, you see over here, some of them, some of these squares are white, some of these squares are gray, some of these squares are completely black. Okay, so what is it? That is the 0 to 255. So black. So if you see a black one over here, let's me. Oh, I can't point over here. Fine. So if you see a completely black square, so that's 0. Completely white square, that will be 255. A very deep gray that may be around 200, 190, a very light gray, okay, just near the whites, the light gray, they may be around 10, 30, 40, something like that. So depending on the value of the matrix element, you have the brightness of the pixel. That was our pixel grayscale image. Now what happens in color images? Now I can explain you with my tab as well. We have three scales. Something interesting. Look over here. There's a choice for me to choose the color of my pen. Okay. There's red. See the numbers. Red goes from 0 to 255. Right? Green can grow from 0 to 255. Blue can grow from 0 to 255. Okay. So there's this RGB color indexing. Okay. So you have heard of RGB quite often. So what is actually happening? Okay, so fine. So what is happening is that you have one matrix. This matrix, let's say the matrix is R. Let's say it's 100 cross 100. So you have 100 rows, 100 columns. So this matrix by itself alone is not a red black is not a colorful image. This, if you see alone, it contains numbers from 0 to 255, so it's a black and white image on its own. Then there's another plane, that's the green plane, that's also 100 cross 100. So you also have these matrices, the pixels and the numbers, and then you have the blue. So in the blue also you have a corresponding matrix of size 100 cross 100 from 0 to 255. That also has these elements. So now what happens? You have red LEDs. I'm just giving an example. Red LEDs, green LEDs, blue LEDs at a position I comma at the ith row and jth column. What do? I mix red with the intensity described in the this matrix. I mix green with the intensity described by the element Gij, and then I mix blue with the intensity Bij. Okay, and then the resultant color is the one that I get. In order to make things clear, if I put Rij equal to 0, Gij equal to 0, Bij equal to 0, I get black color. If I only put Bij equal to 255 and rest all is 0, I get this color. Okay, so let me do a color coding, that would be good. Similarly, if I do only Gij equal to 255, rest all of them 0, I'd get a green color. Same with red, Rij equal to 255, rest all 0, I get red. Now if I mix all of them, I get a white color back. So that's how you are able to look at color images. So there's a whole course called image processing, which people take in their 4th year as electives, and in some other colleges also people learn this in their 1st year. So if you are interested in computer vision, deep learning for image processing, this becomes a fundamental thing. So this is also a mathematical representation of the signal. So that was somebody was asking about image signal, image and picture. Yeah, image and picture is same. And now when you talk about video, we have this dimension of RGB, which is the picture, and then each of these matrices RGB. Okay, so you may have in your camera when you take photo videos, you may have heard of this term 30 frames per second, 60 frames per second, which is called the frame rate. What does the frame rate say? Frame rate describes the number of frames, the number of such single snap images that you take in 1 second. Okay, so if you have say frame rate of 100 frames per second, so that means in 1 second you are capturing 100 images. So the time interval for one image will be 1 upon 100 seconds. Okay, so that's around 0.1 second. So in first second you send this RGB, so after that some movement took place, you send the next RGB after 0.1, or you capture the when you are sending photo or you're capturing photo, then after next 0.1 second you send RGB. Okay, you capture this RGB. Okay, so this is the video. Okay, so when you're taking the video you are actually capturing all this data. Why do say people say megapixel count is not everything? So actually it goes quite deep into something called computational photography, and I do not work in this field, so it's goes into lens optics and all that, so I won't be able to say you. So I am the wrong person to ask this question. Maybe when you take an image processing course or some computer graphics course, then you can ask some NPTEL expert over there. But as of now, I am the wrong person. Maybe you can ask ChatGPT. He can help you. It can help you. Okay. So any other doubt as of now? We just have 11 minutes in hand. Please let me know. Otherwise, we can conclude today's session. Any suggestions, anything that you want me to cover, especially in the upcoming sessions? So for those who came in late, my name is Shouharda Ghosh, and okay, so my contact details if you want to. Okay, so any doubt that you have related to PMRF session, please okay, send it to me at shouharda dot @iitgn. So you are asking, are exam dates fixed? So generally NPTEL fixes the exam dates. But in case you have some clash or all, you need to check with the coordinators. I won't be able to answer anything. Yeah, so anybody watching this live stream, or those who will be watching it in the recorded version, please let me inform you that I won't be involved in any of the setting of the upcoming assignments. Okay, I have no idea about what will be sent. I don't have any idea about the kind of questions that will be asked in your final exam. Okay, I'm in no way connected with that, because I'm just a PMRFTA, just for answering the previous year previous assignment questions, as well as your doubts, clearing your doubts in this session only. And yeah, so upcoming assignment questions, I have no idea. Previous year's question papers, final exam question papers, we have no access to that. Upcoming exam question papers, we have no access to that. We have no connection with um, the course faculty involved in this course. Okay, so this is something important to remember. So I neither I have any sample reference question paper for your exams, nor I will be able to provide you the same. So a lot of times people put this question that, oh, why aren't you solving previous year questions? Simply because we don't have access to that. So that's it. So anything related to your registration, exams. Okay, so I won't be able to handle any of them because we are not a part of this team. We are just the teaching assistants for the PMRF sessions. Those doubts will be actually covered by the TAs of that NPTEL course. Okay, so any further doubts? Should I close the session now? Pawan, Anjali, Shravan, Govindraj, Mr. Datta, Priya Kumari, Tejaswini, Vaishnavi, Valarmati. Anybody anything to share, anything to ask, any confusions? If not, I shall conclude today's session.